All right, and we're back. All right, so we went through, we defined mu, we defined sigma squared, we defined mu hat. We showed that mu hat is an unbiased estimator, and we found the variance of mu hat. So now we want to, so that's sort of actually all laying background. The thing that we want to do now is we want to define this sigma hat squared term, and then we're going to find what it's equal to. So sigma hat squared, or the pseudo-variance, or average squared sample deviation, is equal to the average of the squared deviations, the difference between a point and the sample and the mean of this sample. So this is exactly as we defined it in that first video that I made. Sort of a naive way to approximate the in a naive way to capture how spread out some data points are. Also note that we're using mu hat minus mu hat instead of mu in this expression, and this is where the problem comes in. If we knew the true population value of mu, we could insert that in, and that would be an unbiased estimator. However, we usually don't have the population value of mu, and so we have to use mu hat as an approximation. So then we ask, what's the expected? So, yes, I just want to highlight that this is like a pretty intuitive way of measuring the spread, as I talked about in the first video. The sum of xi, we're just taking the average squared deviation of all of the points in the sample. So for every sample, we ask how much it's how far away it is from the mean, positive or negative. Then we square that so they're all positive, and then we take the average of that value. Take the average squared deviation. So we take the expected value of both sides, and we can factor out the averaging part of the expression from the expected brackets, since the expected value of that term is constant, right? So basically we're first factoring out the 1 over n because that's constant, and also we are then distributing the expectation to every term in the sum. So now we have xi minus mu hat squared, and so we can FOIL and just expand and actually multiply that term by itself. And when we do that, we end up with sigma hat squared is equal to xi, maybe xj, it's fine, equivalent, xi squared minus 2 times xi times mu hat plus, excuse me, did I have the expected values there? Sigma hat, the expected value of sigma hat squared is equal to the expected value of xi squared minus 2 times the expected value of xi times mu hat plus the expected value of mu hat squared. So this is what we want. We want to, we're going to, the bulk of this proof is we're going to expand each of these three terms and sort of figure out what they are at base level and then recombine them down here, right? So each of these is solving for one of those terms. When we know what the expected value of sigma hat is, then we can see exactly how biased or not biased sigma hat squared is as an estimator for sigma squared. So we take the first one, xi times the expected value of xi squared And in order to do this, we're actually going to need to substitute using the thing that we skipped earlier. So we can derive the expected value of xi squared from the fact that sigma squared is equal to the expected value of xi squared. So the way we do that is first we just expand, right? So again, xi squared minus mu, xi minus mu squared is equal to xi minus mu times xi minus mu. So we're just expanding here, and then we can FOIL. So we have xi squared minus 2 mu times xi plus mu squared. We distribute the expectation across the sum terms. So we have sigma squared is equal to the expected value of xi squared minus 2 times the expected value of mu xi. Remember that 2 is a constant, so we can pull it out of the expectation, plus the expected value of mu squared. Because expected value is linear, we can pull out the constant multipliers from the expression. And so we know that mu is constant, right? Where it's the population, it is the population mean isn't going to change across doing these sums or doing these manipulations. Population mean stays the same. So that means that the expectation of mu squared is just equal to mu squared. Similarly, we can pull the mu out of this expectation, and so now we're left with sigma squared is equal to xi squared minus 2 mu times e to the xi plus mu squared. And so now we're just going to substitute the value of mu back in. Is that right? Going to substitute the value of mu. Yeah, we're going to substitute the value of mu for. We're going to substitute mu for the expected value of xi. So we end up with the expected value of xi squared minus 2 mu times mu plus mu squared. You can rewrite that as the expected value of xi squared minus 2 mu squared plus mu squared. And we substitute. What are we substituting? This is not substitution. It's arithmetic. Right, so we have 2 negative mu squares plus 1 positive mu squared, so they cancel out. We have 1 negative mu square. And from there, we can just rearrange the terms so that we find that the expected value of xi squared is equal to mu squared plus sigma squared. Right, so we take sigma squared, put it on this side, subtract from both sides, and then subtract the expected value of xi squared from both sides, and then divide by -1 so that we have things positive. So great, now we know the expected value of xi squared, so the expected value of a random draw. We never actually needed this. The expected value of a random draw times itself is equal to mu squared plus sigma squared. I also suspect that there's a way that I could learn to see this at a glance, basically. Like this sort of seems like the deepest, like most important sense of what sigma squared means. It's the thing when you take It's the difference between when you take when you take a single data point and you multiply it by itself in expectation, sigma squared is how much you're deviating from the mean squared. In any case, well, this is one of the things that we need to solve for here. So we just follow this line. And so the expected value of xi squared is equal to sigma squared plus mu squared. So great. One of those was pretty easy to solve for. Second one, the expected value of xj times mu hat equals the expected value of xi times one over n times the sum of xi. All right, so the thing that we're solving for here is we have this term -2 times the expected value of xj times mu hat. Right, that's the thing that we want, and we're starting out by just substituting, because we know we can substitute in the value of mu hat. Right, if we follow this curved line up, we get the value of mu hat is equal to the average of all of the points in your sample. So great. We have is that better? It's not obviously better. So we distribute the outer xi into every term of the sum. So we have the sum here, and we're going to notate that xi as xa so that we can keep in mind that they are different random draws. Also, importantly, xa is an unknown constant here. We're only looping over xi. So this is a sum from sum over I from 1 to n. And for every I, we're taking xi and we're multiplying it by xa. But xa doesn't change. Xa, we took one random draw to get xa, and we're using that one over and over and over in the sum, where xi is changing for each iteration of the sum. And so that's an important difference that we want to keep track of. Also, it seems like there might be something tricky here, because isn't this multiplying? Okay, yeah, so we might be like, well, isn't this multiplying by n? We're multiplying the outer xi, what we called xa, as n. But yes, that's true. In fact, in the original equation, we were always going to do that, because these are just all being multiplied together. We're just distributing this xi into the parentheses, more or less. So we remove the n over 1 constant from the expectation, because n over 1 is constant. And then we distribute the expectation to every term in the sum, as we've done several times before. So this is similar to the thing that we saw over here, except now we don't have a matrix, we just have a single row. This sum, instead of looping we're just looping over I. We're not looping over I and j. Right? A is a constant. So the sum of looping over xi in the sample. So in this sample we took one data point, and then we're multiplying one random data point, and we're multiplying that random data point by all of the other data points in the sample, including itself. So there's exactly one data point for which I equals a, and for that data point, xi times xa equals xi squared. We could also say xa squared. And so we're going to factor that one out. So in this did we drop an expectation there that we shouldn't have? So now we have maybe we did drop an expectation that we shouldn't have. In any case, we have a sum of the expectation of xi times xa. So a particular random draw times every random draw in the sample except itself, and a random, and let's say xa times itself. So that particular random draw. Note that we don't know what xa is, and it could be anything. We're just talking about the structure here without talking about sort of how the values are filled. And notably, we're skipping j equals not j, I equals a equals I in this sum, because it's covered in this case. All right, the question is, do I need an expectation there? I think I do need an expectation. I don't know why it would come out. This is not a constant. xa is not a constant because it could be any random draw, and so xa squared is not a constant. And so we can substitute for xi squared. Right, there's even an expectation there. So remember that xi and xa, the I and the x there is just variables. It doesn't matter which they are. So we can substitute in the value of the expected value of xi squared for the expected value of xa squared. And we get the expected value of j times mu hat is equal to 1 over n times mu squared plus sigma squared. Plus the sum of the expectation of xi times xa. So we resolved that one term that we pulled out. Since this sum excludes the point where I equals a in expectation, xi is as likely to be above or below the mean as xa. By an argument similar to the semi-rigorous, that's not how rigorous is spelled, is it? How do you spell rigorous?
Rigorous. R-I-G-O-R-O-U-S.
Rigor. Intuition pump. In another leg of this proof, that's this one. Right. So if we had kept in the place where the thing is squared with itself, the squaring with itself is sort of a maximizing sort of thing to do. So for one thing, it makes things positive. So even if you have something that's very negative, and you square it with it won't cancel out in expectation if you square it with itself, because two negative things are just very positive. So the bigger a thing is, yeah. So that would mess up the sort of symmetricality above and below the mean. But in this case, because xi is not equal to xa, we, in expectation, it's just a random draw, and each one is as likely to be above or below the mean in expectation. So in expectation, the value of xi times xa is equal to mu squared. Might be above, it might be below, but in expectation, it's equal to mu squared. So that gives us, so we substitute mu squared into that sum. Because the sum is looping over from 1 to n, but skipping the value of I minus a, we are looping n minus 1 times. So here's where this n minus 1 first comes in. Mu squared is a constant, and so summing it with itself, n minus 1 times, is equivalent to multiplying by n minus 1. So now we have the expected value of xj times mu hat equals 1 over n times mu squared plus sigma squared plus n minus 1 times mu squared. We can simplify that, canceling out the mu squareds. Is that right? Plus mu squared plus sigma squared plus n minus 1 times mu squared. Right. Yeah, so the thing that we're doing here is we distribute the n minus 1. Excuse me, n over the 1 over n. Distribute the 1 over n. 1 over n times mu squared plus sigma is just equal to am I thinking about that right? Let's work this out from scratch. Oh, that's not what I want. All right, so 1 over n times mu squared plus 1 over n times mu squared plus sigma squared plus 1 over n times n minus 1 times mu squared (1 over n times n minus 1 is equal to n minus 1 divided by n squared plus n minus 1 times mu squared plus, excuse me, not 1, n minus 1, but, all right, right, okay, so we have 1 over n times mu squared plus n minus 1 over mu squared, and n minus 1, okay. 1 over n plus n minus 1 over n is equal to 1. Yeah. 1 over n plus n minus 1 over n is just equal to 1 over n. Excuse me, it's just equal to n over n. So n times mu squared. N over n, which is equal to 1. And that's right. N over n is equal to to 1, so we have 1 mu squared plus 1 over n sigma squared. Cool. And so that is the second part of our overall thing to solve for. The last part is mu hat minus mu squared. What's the expected value of mu hat minus mu hat? Excuse me. This is the thing that we're solving for. The expected value of mu hat squared. Expected value of mu hat squared. But we're not going to solve for that directly. Actually, we're going to get to that down here. But we're gonna do some work first. So we're going to start with the mu hat minus mu squared. So mu hat minus mu squared is equal to mu hat minus mu. We can FOIL. That's equal to mu hat squared minus 2 mu hat times mu plus mu squared. Then we can take the expectation of both sides. The expectation of mu hat minus mu squared is equal to the expectation of mu hat squared minus 2 mu hat mu. Yeah, we're just taking the expectation of both sides. Then we distribute the expectation to all of the sum terms. So the expectation of mu hat squared minus 2 the expectation of mu hat times mu plus the expectation of mu squared. And for a given population, mu is constant, so the expected value of mu squared is just mu. This is in magenta because I was somewhat uncertain about it, but I'm Changing it back to blue. And so the expectation of mu squared turns into just mu squared. And also, we can factor it out of this expectation here. So now it's here. And this is convenient because what are we doing here? Remember that we are looking for, what are we looking for? Mu hat squared, the value of mu hat squared. And we have it in here. And we're going to substitute in, so we're going to solve for mu hat squared here. Also, now we have just the expected value of mu hat, which conveniently we've already solved for. The expected value of mu hat is mu. It's an unbiased estimator of mu. So now we have the expected value of mu hat squared, which remember is what we're looking for, minus 2 mu times mu plus mu squared, which we can simplify as the expected value of, sorry, I'm a little confused that I did it in this order. I'm going to tinker with this now, copy. These clearly cancel out. Negative 2 wait, the thing that we're looking for. It's 2 mu hat. So negative 2 mu squared plus mu squared is just equal to negative mu square. By simple algebra. And now we're going to substitute in the value of mu hat. No, the value of mu hat minus mu squared. So we know what this expected value is because we solved for it here. So we're just going to take that and put that in here. Taking this. Very good. And so this is mu squared and then from here, pretty surprised that I left this like this. Because my math intuitions are not yet honed. Okay, that's cleaned up slightly. Right, so then we're just substituting that in, and then we take the expected, so now we want to put the expected value of mu hat squared on one side of the equation, because remember that's what we're solving for. So we're subtracting it from both sides. And then we're subtracting n over 1 n sigma squared from both sides. And then we multiply by -1 so that all the negatives balance out. Everything's nice and positive, and we end up with mu hat squared is equal to mu squared plus 1 over n sigma squared. So amazing. Now we can put all of these three legs of the proof together. Right, this leg, and this leg. And combined, we get that the expected value of sigma hat squared is equal to sigma squared plus mu squared minus 2 mu squared plus 1 over n sigma squared plus 1 over n sigma squared plus mu squared. And so we're just going to keep simplifying. To start, so we're just going to keep simplifying. We start by just moving things together. Sigma, mu. No, we're starting by distributing this -2. Yeah. So we end up with sigma squared plus mu squared minus 2 mu squared minus 2 over n sigma squared plus 1 over n times sigma squared plus mu. Mu squared, excuse me. And then the expected value of sigma hat squared is equal to sigma squared minus 2n. So now we're putting all the sigmas together and all the mu's together. And the mu's cancel out. So mu squared minus 2 mu squared plus mu squared is equal to 2 mu squared minus 2 mu squared is equal to 0. Plus 0. And then sigma squared plus 1 minus 2 over n times sigma squared. Right, so because we're just multiplying negative 2n sigma squared plus 1n sigma squared, so that's 1 minus 2 over n times sigma squared. One minus 2 is 1, so sigma squared minus 1 over n sigma squared. And we can treat that as n over n sigma squared minus 1 over n sigma squared, which is equal to n over 1, excuse me. So here's the final conclusion. The expected value of sigma hat squared is equal to n minus 1 over n times sigma squared. So in order to make this equal to sigma squared, in order to change our pseudo variance so that it is a good estimator of our population variance, the thing that we need to do is we need to compensate for this n minus 1 term. And if we put n minus 1 in the denominator, then we put n minus 1 in the denominator instead of n, then they will cancel out and equal 1, and our estimator will, in expectation, be equal to sigma squared, equal to our population variance. That is why standard deviation and variance and population variance have a n minus 1 in the denominator instead of an n. Woo! All right.